Good evening, friends. We'll start page 570. Uniform or localized loss of thickness, all industries. Galvanic corrosion, a form of corrosion that occur at the junction of dissimilar metals when they join together in a suitable electrolyte, such as moist or aqueous environment or soils containing moisture. All metals, with the exception of most noble metals, sorry. All metals with the exception of most noble metals. Temperature range not applicable. Affects critical factors. For GC3, conductors shall be met presence of electrolyte, two different alloys, electrical connector, refer page 465, anything like that. Okay, it's tubes of different materials of TS and baffles, particularly if salt water cooling is utilized, buried pipelines, electrical transmission support towers, and ship halls. These are affecting equipment. Okay. G tubes. Revised groove or pitting corrosion at the bolts of welds. Different materials, refer page 465. Visual inspection of UT gauging. Good design, coating, but more the noble metal shall be coated. So for piping, electric insulating bolt sleeves and gaskets, galvanized steel. Soil corrosion. Atmospheric corrosion. A form of corrosion that occurs from moisture associated with atmospheric conditions. Marine environment, a moist polluted industrial environment with airborne contaminants are most severe. Dry rural environment cause very little corrosion. Carbon steel, low alloy steels, and copper alloy aluminum. Corrosion rates increase with temperature up to 250 degrees Fahrenheit. Above 250 degrees Fahrenheit, surfaces are usually too dry for corrosion to occur except under insulation. Sorry. Critical factors include the physical location, industrial, marine, rural, moisture, humidity, particularly designs that trap moisture or when present in cooling tower mist, temperature, presence of salts, sulfur compounds, and dirt. FF469, F469, general or located, localized depending upon whether or not the moisture is trapped, if there is no coating or if there is coating failure, corrosion or loss in thickness. Can be general. Localized coating failures will tend to promote corrosion. Metal loss may not be visually evident, although normally a distinctive iron oxide rust, red rust scale form. UV, UTR techniques that can be used. Surface reparation and proper coating application are critical for long-term protection in corrosive environment, corrosion under insulation. CUI, corrosion of piping, corrosion, pressure vessels and structural compounds resulting from components resulting from water trapped under insulation or fireproofing. Carbon steel, low alloy steels, 300 series SS and duplex stainless steel, more severe at metal temperatures between the boiling point 212 degrees Fahrenheit to 50 degrees Fahrenheit. Where water is less likely to vaporize and insulation stays wet longer. In marine environment or areas where significant amount of moisture may be present. The upper temperature range where CUI may occur can be extended significantly up to 80 degrees Fahrenheit. Design consideration system, insulation type, temperature, environment, humidity, rainfall, and chlorides from the marine environment, industrial environment containing high SO2 are critical factors. CS low alloy steels 300 SS, 300 SS are also subject to SCC if chloride are present. The duplex SS are less susceptible. Location issues and design issues. CS and low alloy steels lose flaky scale covering the corroded component, highly localized. Visual inspection, profile radiography, thermography, generally appearance will be loose, flaky, corrosion, and prevention, refer 4671. Atmospheric corrosion, oxidation, chloride acid. Cooling water corrosion, general localized corrosion of carbon steel and other metals caused by dissolved salt gases, organic compounds, and microbiological activity. Carbon steel, all grades of stainless steel, copper, aluminum, titanium, and nickel-based alloys. Corrosion occurs in fresh water. In process side, temperature is above 140 degrees Fahrenheit, and in seawater or brackish temperature above 115 degrees Fahrenheit may cause scaling. Fluid temperature type, the water fresh, brackish salt water, and the type of cooling system runs through open circulating, closed circulating, oxygen content high O2, and fluid velocities less than 3 FPS are critical factors. Cooling water heat exchangers and cooling towers in all applications across the industries: general corrosion, heating corrosion, microbiologically induced corrosion, stress corrosion cracking, and fouling and crevice corrosion. Boiler water condensate. General corrosion of pitting in the boiler system and condensate. Return piping, primarily carbon steel, some low alloy steel, some 300 series SS and copper-based alloys. No specific temperature, depend on various factors of pH, O2, quality of feed water, and temperature. Concentration of dissolved oxygen and carbon dioxide. pH temperature. pH temperature. Quality of feed water and a specific feed water treating system. Corrosion can occur in external treatment system, deaerating equipment, feed water lines, pumps, stage heaters and economizers, as well as steam generators system, both the water and fire sites, and the condensate return system. Corrosion from O2 tends to be pitting type, particularly aggressive in the equipment such as closed heaters and economizers, where there is rapid water temperature rise. Corrosion in condensate return system tends to due to carbon dioxide. Carbon dioxide corrosion tends to be smooth grooving of pipe wall. Water analysis for pH conductivity, chlorine or residual biocides, and total dissolved solids to check for leaks in the form of organic compounds. No proactive inspection method. Deaerator cracking problems can be evaluated by WFM MPI. So wet floors and magnetic particle inspection. O2 scavenging in deaerator in the scale deposit control magnetic maintenance. Magnetite material maintenance treatment scheme doesn't minimize CO2 and condenser return system. An amine inhibitor treatment might be required. CO2 corrosion, fatigue, and corrosive and corrosion erosion. CO2 corrosion. CO2 corrosion results from CO2 dissolved in water in the form of carbonic acid, H2CO3. The acid may be lower the pH and sufficient quantities may promote general corrosion and or pitting corrosion of carbon steel and low alloy steels. Increasing temperature increases corrosion rate up to the point where CO2 is vaporized. The partial pressure of CO2, pH and temperature are critical factors. Boiler feed water and condenser system in all units are affected. Effective gas streams of the shift converters in H2 plants can be affected. Concern usually occurs when the effluent stream drops below the dew point approx 300 degrees Fahrenheit. Corrosion rates are high as 1000 MPa have been observed. Overhead systems have regenerated in CO2 removal plants. Localized thinning and or pitting corrosion of CS and alloys CS may suffer deep pitting and grooving in areas of turbulence. Corrosion generally occurs in the areas of turbulence and impingement and sometimes at the root of piping welds. Monitor water analysis, pH, Fe, etc. to determine changes in operating conditions, RTUT, angle probe, elbows, and T's where turbulence occurs. Corrosion inhibitors in steam condenser and vapor system. Vapor plus increasing condenser to pH above 6 can reduce corrosion. In steel condenser system, 300 series SS and are highly resistant to corrosion in most applications. Selective upgrading of SS is usually required to remove CO2. Removal of units 400 series SS and duplex SS are also resistant. Boiler water condensate corrosion and carbonate cracking. Flue gas dew point corrosion. Sulfur and chlorine species in fuel with from sulfur dioxide, sulfur trioxide, and hydrogen chloride within the combustion products. At low enough temperature, these gases and the water vapor in the flue gas will condensate to form sulfurous acid, sulfuric acid, and hydrochloric acid, which can lead to severe corrosion. Carbon steel, low alloy steels, and 300 series SS. Dew point of sulfuric acid depends on the concentration of sulfur trioxide in the flue gas, but it is typically about 280 degrees Fahrenheit, and dew point HCl depends on the concentration of hydrogen chloride. It is typically 130 degrees Fahrenheit. The concentration contaminates sulfur and chloride in the fuel and the operating temperature of gas metal surface. Determines the likelihood and service severity of corrosion. Since all fuels contain some amount of sulfur, sulfuric acid, sulfurous acid, dew point corrosion can occur if the metal temperature are below the dew point. All fired process heaters and boilers that burn fuels containing sulfur have potential for H2SO4 dew point corrosion in the economizer section and stacks. 300 SS in HRSG, therefore 484. Sulfuric acid corrosion on economizers and other carbon steels, low alloy steel components will have general washed on broad shallow pits depending on the way of H2SO4 condensate for 300 series SS feed water heaters. In HRSG, stress corrosion cracking will have surface breaking cracks and the general appearance will be somewhat cracked. Wall thickness measurement by UT method will monitor the wastage of economizer tubes. Stress corrosion cracking of SS 300 series SS can found using BT and PT inspection. Maintain metallic surface at back end of the boiler and the fire heaters above the temperature of sulfuric acid dew point corrosion. For HRSG, about 300 series SS in the feed water heaters if the environment is likely to contain chlorides. In oil-fired boilers, when units are water washed to remove ash, if the final rinse doesn't neutralize the acid salts, sodium carbonate should be added to the final rinse. The lower temperature hydrochloric acid may condensate and promote HCl corrosion, carbon steels, and chloride stress corrosion cracking 300 series SS. Microbiologically induced corrosion, a form of corrosion caused by living organisms such as bacteria, algae, fungi. It is often associated with the presence of tuberculosis or slimy organic substance, carbon and low alloy steels, 300 series SS and 400 series SS, aluminum, copper, and some nickel-based alloys. Of 235 degrees Fahrenheit. So minus 70 into degrees centigrade to 113 degrees centigrade. MIC is usually found in aqueous environment or service where water is always or sometimes present, especially where stagnant or low flow conditions allow and or promote the growth of microorganisms. Heat exchanger, bottom water storage tank, piping with stagnant low flow and piping in contact with some soils equipment where hydro-test water has not been removed and equipment has been left outside and unprotected. Product storage tanks, water-cooled heat exchangers in any unit where cooling water is not properly treated can be affected. Fire water system can be affected. MIC corrosion is usually observed as localized pitting under deposits or tubercles that sealed the organisms. Damage is often characterized by copsep pits within pits in the carbon steel or subsurface cavities in SS. In cold water system, effectiveness of treatment monitored by measuring biocide residual, microbes counts, visual appearance. Special probes have been designed to monitor for evidence of fouling, which may precede or coincide with MIC damage. Increase in loss of duty of a heat exchanger may be indicative of fouling and potential MIC damage. Foul smelling water may be sign of trouble. Microbes require water to thrive. Systems that contain water, cooling water, storage tanks, etc. should be treated with biocides such as chlorine, bromine, ozone, ultraviolet light, or proprietary compounds. Refer 483. Cooling water corrosion. Soil corrosion. The deterioration of metals exposed to soils is referred to as soil corrosion. Carbon steel, cast iron, ductile iron. Many factors including operating temperature, moisture, O2 availability, soil resistivity, soil type, homogeneity, cathodic protection, stay current, drainage, coating type, age and conditions. ASTM STP 741 as well as APARP 580, publication 581, refer page 491. On-ground piping and equipment as well as buried tanks and the bottom of above ground storage tanks. Ground supports metal structures. External thinning with localized losses due to heating, poor condition of protection. Coating is a telltale sign of potential corrosion damage. Measure soil protection using dedicated reference electrodes near the structure. Cathodic protection, SRP 169, guided ultrasonic thickness tools, pressure testing or visually by evaluation. Soil corrosion of ACS can be minimized through use of special backfill coatings and cathodic protection. The most effective protection is combination of corrosion resistance coating and a CP cathodic protection system. Galvanic corrosion. Caustic corrosion. Localized corrosion due to concentration of caustic or alkaline salts that usually occurs under evaporative or high heat transfer conditions. However, general corrosion can also occur depending on alkali or caustic solution strength, primarily carbon steel, low alloy steel, and 300 series SS. Exposure to high solution strength caustic can be result in general corrosion of carbon steel above 175 degrees Fahrenheit. And very high corrosion rates above 200 degrees Fahrenheit. Also, carbon steel and 300 series SS serious corrosion problems in high strength caustic solution above about 150 degrees Fahrenheit. Major contributing factors are the presence of caustic NaOH or KOH strength and temperature, boiler heat exchangers, crude unit charge where caustic and are added, preheat time exchangers, furnace tubes and transfer lines, units that use caustic for removing sulfur compounds from product stream. Metal loss, metal gouging, deposit grooving. UT thickness gauging injection points should be inspected in accordance with API 570 UT scans. Radiography can be used. Steam generating equipment may require visual inspection with the use of borescope. Proper designing reducing the amount of pre-caustic by ensuring adequate water flooding and water flow. Ensure proper burner magnet to minimize hot spots on heater tubes and by minimizing the ingress of alkaline producing salts into condensers. Caustic injection facilities should be designed to allow proper mixing and dilution of caustic in order to avoid the concentration of caustic and hot metal surface. Caustic corrosion is also referred to as caustic gouging. Ductile gouging, a referred mechanism is known as departure from nuclear boiling DNB as discussed in the stream blanketing. De-alloying. De-alloying is selection of corrosive mechanisms in which all one or more constituents of an alloy is preferentially attacked, leaving a lower density de-alloyed. Often porous structure components failure may occur suddenly and unexpectedly because mechanical properties of the de-alloyed metal are significantly degraded. CU alloys, brass, bronze, alloy 400 and cast iron. Factors include composites of alloy and exposure conditions including temperature, degree of aeration, pH and exposure time. Alloy brasses. Many water, especially stagnant conditions, zinc, grey cast iron, soils, many waters, iron, graphite corrosion, aluminum, bronze, primarily with greater than 8% aluminum, HF acids, chloride ions, seawater, aluminum dealuminification, silicon bronze, high temperature steam and acidic species, silicon desilification, tin bronze, hot brine and steam, tin distal stanification, copper nickel 70-30, high heat flux and low water velocity, nickel, denickelification, monel, hydrofluoric and other acids, nickel, denickelification, UG cast iron piping, HE tubing, and TS cold water, seawater service, boiler feed water, and After boiler components including bronze pumps, Monel strainers and brass pressure gauge fittings. Other color changes are a deep pitched corroded appearance as one element is removed from alloy depending on alloy. Outward appearance and affected material may not be noticeable upon visual inspection, even where the full wall thickness is degraded. Attack may be uniform through the cross section layer type or it can be localized block type. In some cases, no dimensional other visible changes. Change of color depth and scale de-alloying in the brass is usually evident by reddish copper color instead of yellow brass color. Graphitic color tone cast iron charcoal gray and material can be cut or gouged by knife. Metallography reduction of hardness, acoustic tech loss of metal ring and attenuation no UT thickness plus FFS. Altering the exposure condition, replacing it with resistance material depending on the alloy environment combination, cathodic protection or barrier coatings may be effective. De-alloying often referred to or by the element removed as if dezinkification, stanification, de-nickelification, de-aluminification, and graffiti corrosion. De-alloying has also been referred to as selective leaching, graphite corrosion affects cast iron. Graphitic corrosion. Cast iron are comprises of graphitic particle embedded in the iron matrix. Graphitic corrosion in form of de-alloying in which iron matrix is corroded, leaving corrosion products and porous graphite attack result in a porous structure with a loss of strength, ductility and density. Usually occurs under the low pH and stagnant condition, especially in contact with soil or water high in sulfates. Primarily grey cast iron, but also nodular and malleable cast iron experience graphitic corrosion. However, nodular and malleable cast irons tend to crumble when attacked. White iron is not subjected to this damage because there is no free graphite. Damage occurs in the presence of moisture in aqueous phase, usually below 200 degrees Fahrenheit, 93 degrees centigrade. Factors that influence graphitic corrosion include composition of the alloy, exposure conditions including temperature, degree of aeration, pH, and exposure time. Graphitic corrosion can occur soft water, salt water, mine water, dilute acids, and UG piping, as well as in boiler feedwater equipment. Typical examples of excluding feedwater piping pumps, including pump impellers, valves, and UG cast iron pipe. Pre-water systems are particularly vulnerable. May not be noticed in visual inspection, even full wall thickness is degraded. Damaged areas are soft and can be easily gouged with knife or hand tool. Metallography for confirmation. UT not a good method. Acoustic technique, loss of metal and US attenuation, significant reduction in hardness, although affected areas are localized. Internal graphitic corrosion can be prevented by coating and or cement linings. External graphic corrosion may be prevented by external coating or cathodic protection in severely corrosive soil. Knowing potential susceptibility of cast iron is required as difficult predict galvanized corrosion. Also known as selective leaching, graphite corrosion is a form of de-alloying of cast iron. It should not be confused with graphitization, decomposition of carbides at high temperature. Okay, I will stop here, gentlemen.